Hi, my name is Scott Simpson, and today we'll be talking about the solubility product, or it's also known as Ksp. So Ksp is basically an equilibrium constant for when you have an ionic solution dissolved in a solvent, so normally water. So what you try and do is you try and determine if how much of the ions are dissolved in solution. And you can determine this from the equilibrium constant or the solubility product Ksp. So let's look at a sparingly soluble salt that we know will form a precipitate in solution. Let's look at something simple like silver chloride. So we know silver chloride precipitates out in solution, but there will still be some ions that are dissolved in the solvent. So imagine if we have a beaker full of water and we end up plunking in some silver chloride. So what will happen is there will be some solid silver chloride on the bottom, assuming we have a high enough concentration. And then there will be silver cations and chlorine anions also dissolved in the solution. So to determine how much cations and anions are dissolved in the solution, you can use the solubility product. Now, how do we determine this solubility product constant? Well, if we take our solution, or if we take our solid silver chloride, we know it's going to dissociate into a cation and an anion because this is, in fact, an ionic solid. So, let's actually move this a little bit. So, we have silver chloride, AgCl solid, and it exists in equilibrium with 1 Ag plus and 1 Cl minus. So normally you write AQ here just to show aqueous. Depending on your lecture, you may not need to include these AQs since you have the plus and the minus, but it's just good practice to make sure you have the AQs there. And also notice I've indicated that the silver chloride is a solid, so it's a precipitate. So if we were to write out the solubility product for this, we'd have Ksp is equal to, now normally when you do equilibrium constant, you have products over reactants, but when you have a solid or a pure liquid, the concentration ends up being 1 and it cancels out. So it's not included by definition in the equilibrium constant. So these are our products, but since this reactant is a complete solid, we ignore it in the equilibrium expression. So what we end up having is Ag plus and then Cl minus, like that. And that would just be our solubility product for silver chloride. Let's move on to a different example though. Let's look at calcium fluoride. So it's a little different but very similar. So calcium fluoride is also an ionic compound and it's also a sparingly soluble salt. And what I mean by that is it readily forms a precipitate in solution. So let's say we have magnesium fluoride. We'd have 2 fluorines, solid. This would end up splitting up into 1 magnesium 2 plus. We know the 2 plus comes from the periodic table. If you look, it's in the alkali earth metal column. And then we know fluorine has a -1 charge. And we've indicated that we have 2 fluorines, so we need to make sure the stoichiometry matches. And we have a 2 here. All right, so let's write out our equilibrium expression. So Ksp is equal to, so we have to just look at here, and we raise our concentrations to the coefficients that we have. So since there's a 1 in front of the magnesium, it's raised to the power of 1, so we don't worry about it. But if we have a fluorine, since we have 2 fluorines, we have to square this value. All right, so let's say we want to determine how much magnesium and how much fluorine is in solution. Now, what you have to do is you have to look up the Ksp equilibrium constant values in the back of your chemistry textbooks. This it's maybe kind of difficult to see. If it is, I apologize. My markers are kind of crummy and the camera is kind of far away. So we'll try and work with what we have. But the Ksp value of this is equal to 3.9 times 10 to the minus 11. So let's say we want to know how much magnesium and how much fluoride we have. So we have to do something called an ice diagram, or an ice table. So I'm actually going to do the ice diagram down here. I need to check if you can actually see that. You should be able to. So ice, the I stands for the initial concentration, the C stands for the change, and E stands for at equilibrium. So let's draw that out like that, at equilibrium. All right, so initially, before we put any of the magnesium fluoride in our solution, we have 0 initially. So 0 magnesium, 0 fluoride. The change. So we have to determine the change. This is where it comes, algebra comes into play. So we term one an unknown coefficient, and we term the other related to it. So let's, for simplicity's sake, let's say the magnesium is just X. So looking at our stoichiometry, we notice for every one of these, we get 2 of these guys. So if we were to set up a ratio, if we have X number of magnesiums, we're going to have 2 times X number of fluorines. So this is going to end up being 2X. All right. So then at equilibrium, what we end up at, or what we have, is the magnesium concentration will be equal to X. The fluorine concentration will be equal to 2X. So next, we have to plug that into our equilibrium expression, which is this guy that we have right here. So Ksp is equal to our magnesium concentration, which is X, times our fluorine concentration, which is 2X, and that's squared. And that ends up equaling this numerical value. All right, I'm going to erase this part here, and we're going to keep working with this one up top. Now, let's say, well, let's keep going with this. So we need to manipulate our algebra. So we end up with, this term is just X. And in this side, we're squaring 2X. So that's equivalent to 2X times 2X. So if we write this out again, we have X, 2X times 2X is 4X squared. Sorry, I need to draw that a little bit bigger. X squared. Now if we multiply these together even further, we end up with, I think I need to switch markers now, 4X cubed. And what was our value equal to? So we have a Ksp value equal 3.9 times 10 to the minus 11. Sorry, had to check my reference book here. All right, so we're trying to determine what is the concentration at equilibrium. So if we end up doing this, we have to manipulate our equation around. So x to the third is equal to 3.9 times 10 to the minus 11th divided by 4. And then we have to take the cubed root of this. So 3.9 times 10 to the minus negative 11 divided by 4. I need to go grab my calculator real quickly. So, 3.9 times 10 to the minus 11 divided by 4. So this ends up equaling the cubed root of 9.75 times 10 to the minus 12. I'm going to manipulate this up here. So now we're going to take the cubed root of that. So, cubed root. And we end up with 2.14. I'm going to keep one more significant digit just for calculation purposes, times 10 to the 1, 2, 3, 4, times 10 to the minus 4 molar. All right, that is how much magnesium we have dissolved in solution. If you remember initially, our amount of fluorine is 2x, so we just have to multiply that by 2. So let's get rid of some of this stuff. There we go. So this is equal to our magnesium concentration. And now our fluorine concentration that we defined from our Ksp is equal to 2x, which is equal to 2 times 2.14 times 10 to the minus 4th molar. So we manipulate that a little bit more, just multiply it through. We get 4.8 times 10 to the minus 4th. So, and the common ion effect, which is when you start putting in a little bit more of one solution, how it perturbs the equilibrium and what ends up happening to the concentrations of your reactants in solution. So I hope I've been informative. If you have any questions or concerns, please list them below, and thank you for your time.